I'm going to talk about what I'm going to talk about is based on joint work with Anatoly Grishpan, Dmitry Kaluzhny, Verbovetsky, and Hugo Vorderman. They're all at Drexel University, so to shorten it, I refer to them as Drexel Cube. I'm going to talk about determinantal representation, certifying hyperbolicity and stability. And so let me first of all review hyperbolic polynomial and hyperbolicity cones. I think they were already discussed quite a few times at this workshop and other workshops of the poema. So,
Victor, may I say just one thing?
Yeah.
Sometimes your voice sometimes fades away, so maybe you are moving from the mic, maybe sometimes.
Okay, is it okay now?
Yeah, so at the last word, it was very good. So stay close to the mic, please.
So a homogeneous polynomial P and for now it's b plus 1 variables, real coefficients, and I denote the variables x0 through xd, is called hyperbolic with respect to a point A in Rd plus 1 if P of A is not 0, and for any B in Rd plus 1, the one variable polynomial, so we restrict our polynomial to a straight line through A in direction B, has only real roots. And geometrically, if I denote by V the variety, the complex projective variety defined by my polynomial, so here for a point I use square brackets to define point with the given projective coordinates, and if I denote by VR the set of its real points, so the points with real coordinates, then what I'm saying is that the points with A is not on, and if I take L intersection with V, it's going to intersect only real points for any real straight line L through A. Okay, and there are, by the way, two very nice surveys that maybe I should mention. So, two nice surveys. There is by Harvey and Lawson in 2013, I think, and by Determinantal in 2012. Okay, so they were introduced by Garding. In 51, I think. And Garding himself refers to Petrovsky. And the amazing thing that Garding discovered was that there is a convexity hiding there, who proved the following, So if we look at the connected component, C or CPA of the point A in the set of all x's such that Px is not zero. So kind of we take the point A, P of A is not zero, and we move as long as P of X is not zero. So this connected component is a convex cone. In fact, it can be identified as the set of all points B in Rd plus 1, so that when we look at the restriction of the polynomial P to the straight line through A in direction B, then all the roots of this polynomial are not only real, but they are positive. So that's an alternative way of identifying this connected component. And C was hyperbolic with respect to A. In fact, C is hyperbolic with respect to A prime for all A prime in C. So hyperbolicity persists within this C, and the C is called a hyperbolicity cone. And of course, the same hyperbolicity cone can have more than one defining polynomial, because you can take P times any polynomial which is hyperbolic with respect to Q and whose hyperbolicity cone contains C. But of course, the minimal or irreducible hyperbolic polynomial P with hyperbolicity cone C can be recovered just because we look at the boundary of C, we take it Zariski closure, and that's exactly will be the real points of the corresponding variety. And before moving on further, let me just mention the geometric or the topological picture. It's actually very simple. So geometric or topological picture. So if the corresponding variety, at least the real points, is smooth, and we can always deform our polynomial so that it is smooth, then VR is isotopic in the ambient space to a disjoint union of n over 2 concentric spheres. Here n is the degree of P. If n is even and to a disjoint union of n over 2 concentric spheres and hyperplane, if n is odd, and the interior of the innermost sphere corresponds to hyperbolicity cone. Well, in this case, it's actually unique hyperbolicity cone, so it's the hyperbolicity cone. So the picture, if we take the case of 3 homogeneous variables, so dimension is 2, and if I can then draw the affine picture, if you wish to take a plane cut, so that I can actually draw a picture, it looks something like that. So that's the innermost circle, that's the hyperbolicity cone, and then there will be some others. Oops. So here, these 2 and n, I guess, is 7. So there are 3 spheres and the hyperplane, and the point is, of course, if I take any point in the innermost sphere, and if I take a real straight line, then it will have to intersect each one of the spheres on the outside. So there will be, this drawing here is not good. So there will be, since there are 3 spheres, since there are 3 circles and the line, that already gives you 7 points of intersection, 2 for each circle and 1 for a line, and that forces all the intersections to be real. So that topological picture forces hyperbolicity, and that's always what happens. Okay, so that was a quick reminder about hyperbolic polynomials. Now, what about how determinantal representations come in? Well, how can we certify that the polynomial is hyperbolic, or how can we produce a hyperbolic polynomial? So how to construct hyperbolic polynomials? Well, the simplest example are determinants. So if I take A1, A0, A1, AD, some n by n real symmetric or complex Hermitian matrices, and if I assume that A0, A0 plus A1, A1 plus AD, AD is strictly positive, then it is easy to see. Basically, it's just the fact that eigenvalues of a Hermitian matrix are always positive, that if I define P to be the determinant of x0 a0 plus x1 a1 plus xd ad is hyperbolic with respect to A, and the hyperbolicity cone CPA is just the set of all x's in RD plus 1, where the matrix pencil is positive definite. So this is a so-called spectrahedral cone. An intersection of a linear space with the cone of positive definite matrices. And the so-called generalized Lax conjecture tells you that that's all there is. So generalized Lax conjecture is that any or every hyperbolicity cone is spectrahedral. So any hyperbolicity cone can be given by intersection of a cone of positive definite matrices with a linear subspace. In terms of programming, of conic programming, what it means that hyperbolic programming, so I didn't mention it, but probably it was mentioned in some other talks, that hyperbolicity cones are important in optimization because they are very nice cones to use with interior point methods, because if P is the corresponding defining polynomial, then minus log P is a good self-concordant barrier function. And what the generalized Lac conjecture says, that at least as far as feasibility domains go, a hyperbolicity cones, the hyperbolic programming is kind of has the same strength as semi-definite programming. Of course, it doesn't mean still that the two are equivalent, because there is the question of the size of the matrices, the complexity, etc., etc., etc. But at least it means that the feasibility sets, anything which is a feasibility set for hyperbolic programming, is a feasibility set for semi-definite programming. Okay, now what does this mean on the level of polynomials and determinantal representations? Well, it doesn't quite mean that any hyperbolic polynomial admits such a positive definite determinantal representation, because we can allow an extra factor. So equivalently, if P is hyperbolic with respect to A, with the corresponding hyperbolicity cone C, there exists Q hyperbolic with respect to A, with hyperbolicity cone containing C, such that P times Q is such a determinant where the matrices are Hermitian and the linear combination is positive. Okay, so that's the statement. Now, if we are in 3 homogeneous variables, so dimension 2 really, or homogeneous dimension 3, this is actually true without extra factor Q. So this was the original Lax conjecture. From, I guess, 958. And there were partial results of Dubrovin in 83, and of myself in 93. And then this was proved by Bill Hanton and myself in 2007, and then there were by now there are quite a few other proofs. So there is work. There was a proof by Hanzelka in 2014. I gave another proof in 2012. There is a proof by Plowman and Vinson in 2013, I think. There is yet another proof, quite elementary, by the Drexel crowd and myself, 2016. There is been a proof by Greg Nees in 2016 using operator theoretic methods, and there might be more. What I want to mention is that not only this is true, but also it's by now, it's not that there are certainly open questions, but certainly the construction and classification of positive definite determinantal representations of homogeneous hyperbolic polynomials in two variables is reasonably well understood. Again, there are still very interesting open problems, especially computational problems, but all in all, the problem is by now reasonably well understood. Okay, now that's for d equals 2. For d greater than 2, we certainly need in general an extra factor. Otherwise, it's simply false, except for the case of dimension 3 and degrees 2 and 3. So if d greater than 2, in general, we need an extra factor q. And what makes it interesting, so that obvious choices of q will not work. And the simplest choice, where we take q just to be the power of the original p times the power of a linear form, will not work in general. So that's the results of Netzer and Tom, that the linear factor will not help, and the fact that the powers of p will not help is a very deep counterexample using Matroid theory of Brandon. So that's, I think, 2011. Okay, now what are the good news? Well, the good news is that we can get some determinantal, some positive determinantal representations for d greater than 2. So a result of Mario Kummer from 2017, well, the paper is from 2017, says that if p is hyperbolic with respect to A, and there is a smoothness assumption with VR smooth, there exists Q which is hyperbolic with respect to A, such that P times Q is equal to the determinant, does have a positive determinantal representation. So what is missing here, comparing to the generalized Lax conjecture, is there are two things. First of all, we have no control of the hyperbolicity cone of Q. We know that it can contain A, but nothing beyond that. And second, there is the smoothness assumption on V. And the result that I want to present today is that if P is hyperbolic, with hyperbolicity cone C, and I take D plus 1 linearly independent points in C, so the basis of the ambient space, then there exists Q, hyperbolic with hyperbolicity cone containing those points, V1 through Vd plus 1, maybe I should denoted them, should have denoted them V0 through Vd, such that P times Q equals, has a determinantal representation, and the linear pencil XA is positive definite at those points. So I can get a determinantal representation with an extra factor, no restrictions on the smoothness, arbitrary hyperbolic polynomial. I cannot get what I want, the full hyperbolicity cone, but at least I can get a polyhedral cone in there with a maximum number of linearly independent extremal rays. Okay, if you change coordinates, then of course we can just take V1 through Vd plus 1 to the basis, to the standard basis vectors. So what I'm saying, maybe a little bit more concretely, equivalently, assume P is hyperbolic with hyperbolicity cone strictly containing, so the open hyperbolicity cone contains the closed positive orthont. So with hyperbolicity cone C containing R plus closure to D plus 1, so the unit vectors are in the hyperbolicity cone, then there exists Q such that P times Q is the determinant of x0 a0 plus x1 a1 plus xd ad, where all the a's are strictly positive. That's an equivalent statement. Okay, how much more time do I have?
You have about 10 to 15 minutes.
10 to 15 minutes. Okay, good. So let me try to speed up. So the proof is based on connection between not looking actually for certificates for hyperbolicity, but looking for the certificates for stability for complex stable polynomials. So certificates for stability Okay, so in general, if a polynomial P, complex polynomial, and now I denote the variables by Z, and I denote the number of variables by D now, since I'm in the non-homogeneous setting. So P is called omega stable, or omega is an open set, if P has no zeros on omega. And the two most important cases, maybe the most important cases, are where I take omega to be the product of d copies of the upper half plane. And so for the case d equals 1, that's the classical topic which goes back to Hurwitz and Dermit and others. And for d greater than 1, there was also a lot of work, but in particular, there has been a very deep work by Borsi and Brandon. And there is a nice survey by Wagner in the bulletin in 2011. And this is quite related to hyperbolicity in many ways, but in particular a way which is particularly suited for what I want to say. So this is related to hyperbolicity. Hyperbolicity. So if P has real coefficients and is homogeneous, then P is HD stable if and only if P is hyperbolic with hyperbolicity cone containing the positive orthograph. So that's one way to put a connection between real stability and hyperbolicity. So that's one important special case. And the other important special case is omega, the unit polydisk. So here D is the unit disk. And that's again for D equals 1. This is a classical topic. And for d greater 1 also, it appears in many cases, but in particular, it's been an important player or natural important player in multidimensional system theory. Or in multivariable operator theory. And that's somehow where the ideas for our proofs come from. Okay, so to state the theorem, to state the certificate that I want to, for stability, I need a definition. So those two classes of stable polynomials, HD stable and DD stable, or in the case of one variable, upper half plane stability and unit stability, are of course related by the Cayley transform. So Cayley transform relates the two cases, at least on a conceptual level. So namely, zeta is I1 plus zeta tilde over 1 minus zeta tilde with inverse transform zeta tilde equals zeta minus I over zeta plus I. And here zeta is in the upper half plane and zeta tilde is in the unit disk. So that's basic complex analysis. Now, more concretely, what we can do with that is that if P is HD stable, we can define, well, we basically apply the Cayley transform in every variable. So we define P tilde of Z1 tilde, ZD tilde. So I'm going to take P and apply the Cayley transform in every variable. So that's going to be I 1 plus Z1 tilde 1 minus Z1 tilde, I 1 plus ZD tilde 1 minus ZD tilde, and will clear the fractions. So 1 minus Z1 tilde over 2I to the n1, 1 minus ZD tilde over 2I to the power nd, where ni is the multi-degree, the degree with respect to the I of P. And then P tilde is DD stable, that's quite obvious. And we can recover P from P tilde. And P is called strictly HD stable if P tilde is strictly DD stable, meaning that it does not vanish, including on the boundary of the unit disk. Now, what it means is that the original polynomial P is zero-free on the entire upper half plane with the boundary, so HD closure, but we also impose some kind of non-vanishing condition at infinity. And now those non-vanishing conditions at infinity are a little bit tricky to analyze, but what is true, in particular, P is strictly HD stable if it does not vanish for all z's in HD closure, And if we look at its leading homogeneous component, right? So it's a polynomial of degree n, so it breaks into a part of homogeneous pieces. It's non-zero on all the basis vectors. Where Pn is the leading homogeneous component of P. Okay, and now before I finish, I will state the stability certificate that we have for strictly HD stable polynomials. So stability certificate for strictly HD stable polynomials. Which says that assume P in C Z1 ZD is strictly HD stable, then there exists Q, HD stable, such that P times Q is a constant time a determinant of A0 plus Z1A1 plus ZDAD. So here C is a non-zero constant. A0 is a complex matrix which is dissipative. So the imaginary part of A0, which is 1 over I of A0 minus A0 star, is not negative. In fact, in this case, it's going to be strictly positive. And A1 through AD are Hermitian matrices, which are non-negative, and their sum is strictly positive. Now, the point is that this is clearly a certificate for stability, because if a polynomial has such a representation with an extra factor, then if you take any z's in the upper half plane, what you have here will be a matrix. What you have here will be a matrix with a strictly positive imaginary part. And the matrix with a strictly positive imaginary part is invertible. So the determinant is not zero. So this is clearly a certificate for stability, the same way as its positive determinantal representations are certificate for hyperbolicity. And the claim is that assuming strict stability, this is enough. Okay, I have to finish, so let me just say a few things. So first of all, we do not know, it's an open question, whether so open question, is this true without strict stability? The problem is that, of course, you can approximate any polynomials but strictly stable polynomials, but as I might say in the remaining negative amount of time, we don't have control of the degree, so the degree can blow up. It's a usual kind of problem in this type of questions. And for d equals 2, This is true without strict stability and without an extra factor. True without extra factor Q. Kind of the usual thing about the determinantal representations. They are well behaved in degree 2. And this is essentially a result. Well, yeah, let me mention the kind of the chronology in a minute. But there is no, so it is true, but no understanding of classification of certifying determinantal representation. So unlike in the case of the Lax conjecture, where we have a good understanding of what do all self-adjoint positive determinant representations look like, here we know that one exists. There is a somewhat explicit construction. One could argue how explicit it is, but certainly no understanding of what's going, no deep understanding of what's going on. And how is this related to hyperbolicity? Well, the relation to hyperbolicity comes from the fact that, and that's, well, the next to last word that I think that I will say, notice that if we have a determinantal representation as above, you see the highest, oops, there is no Z0 here. The highest degree, this will be a polynomial whose total degree is the size of matrices. Its highest degree homogeneous component will come from here. And that's, of course, a positive definite determinantal representation. So if you have such a determinantal representation, then Pn times Qm up to a factor is the determinant of Z1A1 plus ZDAD, where Pn, Qm are highest degree homogeneous components of P and Q. And now the way the result on determinantal representations of hyperbolic polynomials that I started with is proved now is that you take a hyperbolic polynomial whose hyperbolicity cone contains the positive orthant, and it's not very hard to see that you can shift it a little bit to get a stable polynomial, which will be strictly stable and whose highest degree homogeneous component will be my original hyperbolic polynomial. And then we write this determinantal representation of our stable polynomial, and then it's the homogeneous part gives me the determinantal representation of the original hyperbolic polynomial. I'm not sure if I have -2 minutes or -7 minutes. So let me just say one word about the proof. So the proof proceeds by the Kelly transform that I wrote before. And the idea of using Kelly transform in this particular setting, in this particular way, is due to Greg Nees, who used it to get an alternative proof of the Lax conjecture using operator theoretic tools. And so this statement here is reduced to a similar certificate for DD stable polynomials, for polynomials that are stable with respect to the polydisk. And that is something that we proved a few years ago using a combination of so-called Hermitian positive Stellensatz, which originally is due to Mihai Putinar, and some tools from multivariable operator theory. And maybe just one last word. Unfortunately, this Hermitian positive Stellensatz, the proof is via GNS construction and the separation argument, and it does not give degree bounds. That's why we don't have degree bounds in this certificate here, and that's why we cannot remove strict stability. Thank you very much.